What on earth could geology tell us about intelligent design? It can tell us if we live on a special planet, or if Carl Sagan was right when he said that we are just sort of a humdrum star lost in some forgotten galaxy in the middle of the universe, and there's nothing special about where we live. So I think that geology can tell us a lot about whether Earth is in fact a privileged planet. Okay, well, it's so great to be with you all here today. Thank you for sticking around till the very end. Because I'm the last talk, that means I have no deadline I have to meet. There's no one after me. So I have a captive audience. You're here as long as I want to take. No, I'll try to keep to time, even though I do want to try to get through a lot of material, and appreciate you guys staying till the end. I was looking forward to coming out to the Dallas conference last year before the snowpocalypse happened, and we had to give it online. So it's great to be with you all in person. So the title of my talk is The Good Earth, Insights from Geology on the Design of Our Planet for Life. And to quote a very important person, you have heard it said that there is design arguments in biology and also in physics and cosmology. But I say to you, we can also make design arguments in geology. Why can't we make design arguments in geology? But what on earth could geology tell us about intelligent design? Well, for one, it can tell us what geological features are necessary to make a habitable planet. It can tell us if we live on a special planet, or if Carl Sagan was right when he said that we are just sort of a humdrum star lost in some forgotten galaxy in the middle of the universe, and there's nothing special about where we live. So I think that geology can tell us a lot about whether Earth is in fact a privileged planet. In sci-fi terms, I'm a big sci-fi fanatic, and I'll give some sci-fi references in this talk, but we might ask the question, what is required to terraform a planet? Terraforming is when you take a dead planet. If you think back to the old Star Trek movies and they were terraforming, you take a dead planet and then you turn it into a planet that is habitable for life. So if we were future explorers of space and we were going to do this, what would it take to terraform a dead planet and turn it into a living one? And I think that this had to be done to Earth to make Earth a habitable planet for us. And in fact, Earth has numerous special properties that are necessary for advanced life, and certainly properties that we don't find anywhere else in our solar system. So let's examine just a few in this talk, starting with Earth's magnetic field. So as John West said, my PhD was in paleomagnetism in South Africa. So I did do quite a bit of studying of Earth's magnetic field during my PhD. And before we launch into this, let's just take a review. If you guys have taken any geology, a very basic review of the chemical structural divisions of the Earth, okay? So the thinnest layer of the Earth is the crust. We're on the crust right now, and it's about 25 miles thick. Below us is the mantle, and it's about 1,800 miles thick. And if you go down to the core mantle boundary, can you see that there? The core mantle boundary is about 4,000 degrees, okay? That's in Celsius. So the liquid outer core comes next. That's about 1,375 miles thick, and its temperature is about 4,400 degrees Celsius. And then finally, we have the solid inner core with a radius of 750 miles and a temperature of about 5,500 degrees Celsius. So you can see that as you go from the center of the Earth to the outside, it's very hot in the center, and it's very not a hospitable place for life, but it gets cooler as you get to the surface. That's going to be very important for some of the things we're going to talk about today. So where is the Earth's magnetic field generated? The Earth's magnetic field is generated in the outer core. And how is it generated? Well, we don't know for sure. We can't go to the outer core, but the outer core is made of liquid iron, as opposed to the inner core, which is made of sort of a solid iron-nickel alloy. And the outer core, because it is liquid, there are currents of liquid metal iron and nickel in the outer core that are driven by the Earth's Coriolis force, driven by different rates at which the Earth is spinning at different radii, as well as by convection due to temperature differences between the inner core and the outer core and the lower mantle. So these forces, the Coriolis force and these temperature differences, are causing convection currents of this liquid metal iron nickel. But because the liquid iron and metal and nickel metal carries an electric charge, these rotating currents of liquid metal generate an electric current. And of course, a moving charge or current generates a magnetic field. So that is how it is thought that Earth's magnetic field is generated in the liquid outer core of the Earth. So why is the magnetic field vital for life? Why does this even matter? Well, there are two major reasons why the magnetic field is vital for life. First of all, Earth's magnetic field acts like a deflector shield. Like in Star Trek, you're deflecting space rays and phasers that are going to hit your ship. In the same way, Earth's magnetic field acts like a deflector shield that deflects the solar wind. That protects our atmosphere from being stripped off by the solar wind, and it also deflects much harmful radiation in the form of solar particles, the solar wind, and also galactic cosmic rays from hitting the Earth's surface where it can damage DNA and life forms. So the magnetic field protects our atmosphere from being stripped off by the solar wind, and it protects life on Earth from being damaged by harmful radiation. And this diagram shows it really nicely. You've got solar wind, which is coming, and when it hits the Earth's magnetic field, it's deflected around it. Actually, what really happens is these charged particles follow magnetic field lines, and many of them will get captured along these field lines, and they will follow the field lines to the poles, where the magnetic field lines intersect with the surface of the Earth. And that's why you get the aurora borealis, and you get the northern lights. Also, you get the same thing in the southern hemisphere. It's because you have these charged particles that are coming through the atmosphere, following the field lines, and they only will show up at the poles. But because there's not really any life at the poles, it's not that big a deal if there's more radiation there. There's not anything living at the North Pole, on the surface at least, or at the South Pole. And so the Earth's magnetic field serves as a deflector shield in this manner. So Earth's magnetic field is vital for life. Fine, I think that's very clear. That's very well agreed. But is Earth special in having a strong magnetic field? I think the answer is yes. I went through all the strengths and magnetic fields of the planets in our solar system. And I actually made this chart back when Pluto was still considered a planet. I decided not to take it off just for fun. I know Steve Myers said he wasn't going to get into that debate. I won't either, but we'll just leave it on here for fun. So Earth's magnetic field is fairly strong. In fact, these are all the planets in our solar system that have a relatively strong magnetic field that is strong enough to shield a planet from solar radiation and also galactic cosmic rays. So you can see Earth is not unique in having a strong magnetic field. But there are different types of planets. We need to understand that. We have the rocky planets, or terrestrial planets, which are found in the inner solar system. These are planets made of silicate rock, and they have nice stable surfaces which can serve as platforms where living organisms can exist. Then we have the outer planets, which are the gas giants. These planets are not habitable because they have very high heat and high pressure. They have atmospheric turbulence, yielding chaotic and high entropy environments. Oh yeah, also there's nowhere to stand. So that is a little bit of a problem if you want to have a nice platform where life can exist. So it's thought, generally speaking, when we're looking at astrobiology, that gas giants are not going to be a good place to find living organisms, and terrestrial planets are where you're going to find them. So these are the planets that do have strong magnetic fields. All the gas giants do, but Earth is the only terrestrial or rocky planet that has one. So if you plot up the planetary diameter versus the strength of magnetic field, you can see that Earth is very unique in that it has it's the only planet with a small diameter and yet a strong magnetic field. So is it rare to have a strong magnetic field in our solar system? No, I would say it isn't. However, Earth is the only terrestrial planet with a strong magnetic field that can shield life from harmful radiation. So in that respect, Earth is certainly special. So let's talk now about a second aspect of Earth, which I think makes it very special and it's very important for life, and that is plate tectonics. I'm a big fan of plate tectonics. I studied it in my PhD, but I was surprised in studying plate tectonics during my PhD. I never really learned about why it is so important for life. I had to read some other books that were sort of outside the scope of my studies to appreciate this. So here's why plate tectonics is important for life. Life in the oceans requires certain key elements like carbon, calcium, sulfur, phosphorus, nitrogen, and many others in order to survive. But these nutrients are constantly being depleted out of the oceans. Okay, so every second of every year, every day of every year, plankton and other marine organisms in the ocean are dying. They're falling down through the water column and being deposited and buried in the sediment at the ocean bottom. This creates a constant stream of calcium carbonate and other vital compounds and elements that are in these living organisms raining down to the ocean bottom, where these crucial elements are locked up in the sediment, effectively depleting the ocean. Okay, so it's kind of like this. Over time, you get all these crucial elements for life that are falling out of the water column and getting deposited in the ocean sediments. And eventually, these elements will be depleted from the oceans. Okay, there will be none of these elements left in the oceans. So, and if things are eroding from the continents into the oceans, the continents will also be depleted. So how do we resolve this paradox? Well, Michael Denton, if you've read some of his wonderful books, he has the book, The Wonder of Water, where he resolves this paradox. He says, the tectonic recycling of oceanic and continental crusts holds the key. Balance against the continual and massive loss of minerals to the seabed, tectonic recycling replenishes the oceans with continental runoff and by the reaction of water with upwelling magma at the mid-ocean ridges. So plate tectonics is what replenishes these important elements and compounds into the biosphere. Let me give you guys a diagram to help explain how this happens. Okay, so here in this diagram, we have shelled organisms and other organisms that are dying with all these important nutrients needed for life, taking them down and getting buried in the ocean sediment. And what happens next? That sediment is then buried at the top of the subducting crustal slab, where it is subducted down deep into the earth, where it then melts. So these sediments are then melting deep in the earth, and as those sediments are melting, all those compounds that were locked up in the organisms of life, they then return to the surface. As the magma raises through the crust, comes back up, and then that magma is then expelled through volcanoes. And what comes out of volcanoes are the same elements and compounds that were locked up in the sediments that life needs. And as these vital nutrients are then expelled into the atmosphere and then also erupted into magma, they are then eroded back into the oceans, or if they go into the atmosphere, it's then absorbed back into the ocean. So you have literally a recycling program on the earth. And this is really cool, you guys. I'm from Seattle, where if we don't recycle, they send us a penalty bill. So I'm really into recycling, I do like recycling, but if I didn't, I wouldn't say. Actually, I will say this. I was in Texas last year, and somebody, for the first time, I never heard the solution. They said, they told me this expression, how do you deal with pollution in Texas? They said that the solution to pollution is dilution. I was like, oh my gosh, I can't believe you could never say that in Seattle. You'd be thrown out of the city. But okay, let's get back to this here. And I do like recycling, by the way. I'm not just saying that. So in this recycling program, you have these key crucial elements that are locked up in the ocean crust. They're then subducted, they come back up, expelled into the atmosphere and into magma, where they erode and they go back into the ocean. So we have this wonderful recycling program. Carbon, sulfur, nitrogen, water, calcium, phosphorus are all recycled, and the oceans are not depleted of these crucial elements needed for life. The book Rare Earth by Donald Brownlee and Peter Warr said plate tectonics plays at least 3 crucial roles in maintaining animal life. It promotes biological productivity. It promotes diversity, which is a hedge against mass extinction. And it helps maintain equitable temperatures, a necessary requirement for animal life. We'll get to that one later. It may be that plate tectonics is the central requirement for life on a planet, and that it is necessary for keeping a world supplied with water. So very important, plate tectonics for life. So how many planets in our solar system have plate tectonics? Anyone want to guess? Hold up your finger. 1. As far as we know, and as far as from our studies of other planets goes, Earth is the only planet that is known to have plate tectonics. Earth is definitely special. Okay, so let's now talk about liquid water, but not just liquid water, but just water in general. Why is Earth special in having water, and especially liquid water? Some of this is going to go, you think you know where this is going, and some of this is going to go where you think you know where it's going, and some of it probably isn't going where you think it's going. So planetary scientists have identified 4 requirements for a planet to have a liquid water supply large enough to sustain advanced life, okay? First, the planet had to capture enough water during the formation of the solar system to make a large ocean. Second, the water had to migrate from the planet's interior to the surface. Third, the water cannot be lost into space during that planet's history. And then fourth, that water has to exist as a liquid. So the fourth one is probably the criterion you're most familiar with, and that is what we call the circumstellar habitable zone. The idea that if you look around the sun, there's a band where there's enough radiation being received by a planet to make sure that the water on that planet will not be frozen in an ice form like it is in the outer gas giants, but it's also not going to be vaporized into a gas like it would be on Mercury or Venus if those planets had water. So the circumstellar habitable zone is sort of that Goldilocks zone where the temperatures are just right to get liquid water. And it's thought that both Earth and Mars are in this circumstellar habitable zone. So this satisfies liquid water, criterion 4. But what about criterion 1, getting water in the first place? It's surprising how difficult it's been for planetary scientists to explain how Earth got water. Water is obviously vital for life, yet explaining how Earth came to have so much water has proven tricky for planetary geologists. In fact, this book, How to Build a Habitable Planet, says this: the Earth is about 1/2 of 1% by weight water. The factors that led to this particular capture efficiency, meaning how did Earth get its water, are not understood. Based on the observation that Earth is depleted in potassium and other moderately volatile elements, those are light elements that tend to prefer a gaseous form at a low temperature, our planet would not be expected to have any water. Somehow Earth got just about an ideal amount of water to support life. And it's not clear how this happened according to our standard models of how the solar system formed. And as I learned in school, the main model for the way planetary scientists think our solar system formed is called the nebular hypothesis. So if we just take this model for the sake of the argument and say, what does this model say about how the Earth formed? Well, according to this hypothesis, the solar system began as a giant nebula composed of dust, rock, gas, ice, and other debris. Gravity then coalesced a huge amount of mass at the center, and as the mass contracted, it began to spin, heat up, and flatten into a disk. And as this process continued, eventually enough mass accreted at the center to produce pressure, which caused fusion in that huge mass at the center, and the sun was born. And that's how it's thought that stars form in general, and our sun was first formed through this accretion of mass at the center of the solar system. So around this disk, the leftover chunks of rock and dirt and gas and dust are thought to have then begun to accrete into protoplanets. And near the protosun, sort of at the very center of the solar system, the denser and heavier material with higher melting points coalesced into smaller, rocky terrestrial planets. However, further from the protosun, the lighter elements and compounds, such as water in the form of ice, also hydrogen and helium and methane, congregated to form the gas giant planets. And so if we take the nebular hypothesis, just for the sake of the argument, what do mainstream scientists say about this? Then lighter elements and volatile compounds like water should not have condensed in the inner rocky planets. Earth should not have this much water. And the way this is described in planetary geology is through a concept called the frost line or the snow line. And you're only going to get water condensing into a form that can be accreted into a planet beyond this frost or snow line, but Earth is inside the frost snow line, so we shouldn't have water here. In fact, a paper in the journal eLife says that a very important concept is the snow or frost line, beyond which volatiles, mostly water, condensed and remained in the solid state as ices. In the early solar system, the snow line was just between the orbits of Mars and Jupiter. Jupiter formed just beyond the snow line, where the surface density of solids, mostly ices, was greatest, while the terrestrial planets formed within the snow line. And this article is, of course, by a name that some of you might recognize, Guillermo Gonzalez, who's publishing an article about habitable planets. So who says that ID theorists don't publish peer-reviewed papers in mainstream journals on relevant topics? Of course we do, of course we do. This is one of those papers. So this concept of the frost line, again, beyond the frost line, you can get ice and water condensing into the planets, but inside of it, you're not going to get any non-gaseous H2O. So we don't have water being locked up as the Earth is forming. And Guillermo Gonzalez, who co-wrote the book Privileged Planet, by the way, which gets into some of these topics, I highly recommend it. He says that the Earth formed in a region of the early solar system that was very dry. Yet Earth's water content today is estimated to be significantly greater than its formation at 1 astronomical unit would imply. The leading theories for the origin of the Earth's water and other volatiles involve their delivery to Earth from more volatile-rich regions of the solar system. Water delivery to Earth from comets, once a popular idea, can only account for about 10% of its crustal water inventory. I can vouch for this. I learned about the idea that water was delivered to the Earth on comets when I was studying geology as an undergraduate, and it's now known that yes, there probably could have been water delivered to Earth from comets, and comets that formed far out in the solar system where water could condense as ice, but it's only going to be a small percentage of the water content that Earth has, and certainly not enough to sustain life, okay? So another article in the journal Science sort of confirms what we're saying here, that Earth, according to models of solar system formation, Earth as an inner solar system planet should have little to no water. Early models of planetary formation predicted that the nebular gas near our young sun was too hot to form ice. Water is vapor, therefore, cannot have easily incorporated into the materials that form the inner rocky planets, Mercury, Venus, Earth, and Mars, okay? So do we have a potential solution to the water mystery of where did Earth's water come from? Well, 2 years ago, in 2020, an article was published in the journal Science, which proposed this hypothesis that water may have been delivered to Earth on enstatite chondrite meteorites that are thought to represent sort of the bulk composition of the inner solar system at the time the solar system formed. And this paper says that the origin of Earth's water is debated. The isotopic composition of Earth suggests that it is composed of material from the inner solar system, such as enstatite chondrite meteorites. The inner solar system was too warmed to have retained water ice. So terrestrial water is thought to have been supplied by hydrated materials that formed in the outer solar system before migrating inward. But they think that these meteorites, which they studied, enstatite meteorites, which are thought to represent the constitution of the inner solar system, that these meteorites had enough water to explain how Earth might have obtained its water. But the problem is we're actually not talking about water here, we're talking about just hydrogen. Unlike comets, this is an article from astronomy.com, unlike comets, asteroids don't lock up water as ice. Instead, they trap its components, hydrogen and oxygen, inside minerals. Really, we're not talking about water, we're talking about hydrogen. Okay, but fine, at least we're getting the components of water. Maybe that's enough. So there's still an outstanding mystery here. If enstatite meteorites formed in the inner solar system, like this paper is saying, we still have not explained how the components of water, the hydrogen and the oxygen, condensed into a solid form in the meteorite so close to the sun. So if these meteorites really did form in the inner solar system, that's fine. We see that they seem to have a lot of hydrogen. It's difficult to account for that, but how did these meteorites end up having so much hydrogen so close to the sun? It's very difficult to explain that. Now, I'll use an analogy to explain what I'm trying to convey to you. Let's say that you go home and you find that your house is full of gold. And you think, oh my gosh, this is so great. There's all these gold bars in my house. How did my house come to have all these gold bars? And then a delivery truck shows up full of gold bars. And you say, oh, okay, it makes perfect sense now. Trucks are delivering gold to my house. Okay, well, fine. But how did the gold get onto the trucks? And why are these trucks delivering gold to your house? You've just pushed the origin of the gold back. In the same way, saying that enstatite meteorites, which formed in the inner solar system, carried the water to Earth, really does not explain the origin of Earth's water, because we don't have a good model for explaining how meteorites, like enstatite chondrites that formed in the inner solar system, got the water to begin with. It really has not explained where the water came from. It's not offered sort of a complete explanation. So I think that this is an outstanding mystery. Maybe planetary geologists will solve this mystery as to where Earth's water came from, but I think it has not yet been explained. But it's not just enough to explain how a planet gets its water. You also have to account for a planet not losing its water throughout its history. That's the third criterion that we talked about. So having water initially is not enough to make a planet habitable. You also have to show that a planet will not lose its water over time. And that's criterion 3 listed earlier. And Earth is special because unlike Mars and Venus, which are very similar to Earth in many other respects, it has retained its water. So why has Earth retained its water and not lost it over time? Well, let's talk about Venus. It turns out that Venus has a very strong electric field, which is about 10 times stronger than Earth's electric field. And the theory is that this electric field has actually pushed oxygen ions to the upper atmosphere where they were lost into space. So Earth does not have a strong electric field, and this phenomenon which happened on Venus caused Venus to lose its water. Venus is incredibly hot, but it's incredibly dry. It's got all these greenhouse gases, but it's not moist. It's extremely dry on Venus, and it's not a place for life to exist. So to quote Stranger Things, you can't spell America without Erica. You can't have H2O without O. I don't know if any of you are Stranger Things fans. So if you lose all your oxygen, you're not going to have water on your planet. I got really into Stranger Things during my PhD. It was the only thing that helped me write my thesis. So what happened to Mars's water? What about Mars? Mars may still have small amounts of water. That's still being debated, and it may turn out that Mars did have a lot of water in the past, and it may still have some water, but most of what water it had has been lost, and what remains is largely not liquid. And there are multiple possible explanations. These include low pressure, temperature, and temperature prohibits liquid water either from being it's either going to be frozen or it's going to be gaseous. And the gaseous water was probably driven by dust storms into the upper atmosphere. And the low atmospheric pressure on Mars, there's almost no atmosphere, caused the gaseous H2O to be lost into space. It's also possible that some H2O was incorporated and buried into minerals in the ground. Okay, so that's a set of proposals as to why Mars has lost its water. So how many terrestrial planets today have large amounts of water? You want to hold their fingers. One, that's right, only Earth. So how many potentially habitable planets have large amounts of water? Again, the answer is one, because yes, there is water in the gas giant planets, but for reasons we discussed earlier, they're not considered to be options as habitable planets. So Earth is very special in being a rocky terrestrial planet and having large amounts of water, and in fact, it still remains to be explained why Earth has so much water. Okay, so let's talk about the atmosphere. So many aspects of the Earth's atmosphere are well designed for life. So everybody take a deep breath, right? Isn't it wonderful that we have this air to breathe? We take air for granted, but we don't appreciate just how many aspects of Earth's atmosphere were specially crafted so we could be here and take those deep breaths. So let's talk first about the idea of atmospheric pressure. Atmospheric pressure, if you think back to your high school physics, is the force per unit area exerted against an object by the air as gravity pulls that air downward towards the Earth, okay? So atmospheric pressure is very important. If we have too much pressure or too little pressure, the atmosphere is not habitable for life. And it turns out that there are many Goldilocks criteria about the Earth's atmosphere that have to be just right or life cannot exist. So what about atmospheric pressure? Well, the air pressure must be light enough to allow for evaporation to happen, and heavy enough to destroy asteroids. Okay, so why are these parameters important? Let me go through these very briefly. Evaporation is important because evaporation is what drives the water cycle. It starts with evaporation from the oceans, and then, of course, the water vapor that evaporates into the atmosphere forms clouds, which then rains upon the Earth. And that, of course, allows plants to grow and allows all the organisms that live on the terrestrial side of the planet to live. And then that water is returned into the oceans through streams and currents and lakes and so forth and rivers. And then it flows back into the oceans where it provides nutrients for living organisms in the oceans, because we all know that fish eat donuts and hamburgers. Okay, so that's the water cycle. If we did not, if the atmospheric pressure was too great, we could not have evaporation to drive the water cycle. What about the atmosphere being not too dense to allow for the destruction of asteroids? Well, between 2000 and 2013, I was really shocked when I heard this. 26 asteroids hit Earth with energies of 1 to 600 kilotons. And just for comparison, the Hiroshima bomb was 15 kilotons, okay? But because of our thick atmosphere, most of these exploded in the upper atmosphere with no damage to the Earth's surface. Okay, so the atmosphere is thick enough to not prevent evaporation, but to destroy the vast majority of asteroids before they hit the Earth's surface. And this is very important for allowing a habitable planet. What about the Earth's gravity related to the atmosphere? The Earth's gravity must be strong enough to prevent losing crucial gases from the atmosphere, like oxygen and nitrogen, but it has to be weak enough to allow for the loss of highly flammable, light volatile gases that are not really that important for life. So in the book, How to Build a Habitable Planet, they explain what we're talking about here. The ability of a planet to hold its gases is strongly dependent upon its gravity. While Earth and Venus are massive enough to hold all but the lightest gases, the Moon and Mercury have insufficient gravity to hold any gas. Thus, Earth and Venus have substantial atmospheres while the Moon and Mercury have none. It's important to have the right gravity to be able to hold on to your atmosphere, but you don't want it to be too strong because there are some elements that you don't want to build up in the atmosphere, like hydrogen or helium. You want those to be lost. What about the composition of the atmosphere? Well, obviously, oxygen is very important for the atmosphere for advanced life. But how much oxygen or how little oxygen? The amount of oxygen also has to be precisely balanced in the same kind of Goldilocks fashion. And it turns out that the partial pressure of oxygen in the atmosphere has to be high enough to sustain biological respiration. Obviously, if there's too little oxygen in the atmosphere, then we're not going to be able to breathe. But if the oxygen level is too high, then actually bad things will happen. Number one is you could have more likelihood of explosions. okay? If the oxygen level is too great, then lightning strikes would actually ignite the atmosphere and cause fires to burn out of control, and there would be huge explosions. Another problem is that too much oxygen is actually toxic to life. This gets kind of serious for a moment, but if any of you have had any friends or family that have been on ventilators or respirators during this whole COVID epidemic, well, you know that it actually is not good to be on pure oxygen for too long. It's highly damaging to a person's body. And in fact, free radicals, this is what the problem of free radicals are. You guys have heard about that. Free radicals will steal electrons from organic materials and damage them. So if we have too much oxygen in the atmosphere, then that is very damaging to life. And this book, Oxygen, the Molecule That Made the World, says that under present conditions, most lightning strikes do not start fires because forest vegetation is damp, especially when electrical storms are accompanied by torrential rain. But if wet organic matter burns freely in the air, containing more than 25% oxygen, as we were told, then given an atmosphere with such levels, lightning could trigger conflagrations even in rainforests. So you don't want too much oxygen or the world will burn out of control. So Earth's atmosphere has about 21% oxygen, right in the sweet spot between 17% and 25%. But what is the other 79% of the atmosphere? I mean, we think, does it even matter? Well, it turns out that it's 78% nitrogen, about 0.9% argon, and 0.1% other gases. So if 78% of our atmosphere is nitrogen, which is not needed for respiration, does this mean that Earth's atmosphere was not designed with life in mind? Is this sort of this arbitrary property of life or of the Earth that's not important for life? Well, it turns out the exact opposite is true. But let's pretend for a moment that we don't know anything about nitrogen, being that 78% of the atmosphere, and we're terraforming a planet. So what gas do we want to have to compose the other 78%? We're going to try to choose a good gas. What constraints are we under for what that gas has to be able to do to make a habitable planet? Well, constraint number one is you need some gas that can dilute the oxygen. Too much oxygen, again, will be very damaging to life and cause huge fires and explosions. Constraint number two is you want that gas to be diatomic, meaning there are 2 atoms per molecule, because monatomic molecules with just 1 atom won't block harmful EM radiation. But triatomic molecules are greater. Those with 3 or more atoms will act as greenhouse gases, and you don't want too much greenhouse effect. Constraint number 3 is the gas must also have a density and polarity similar to oxygen. So it mixes well with oxygen and doesn't stratify the atmosphere. Let's talk about this third constraint very quickly here. So you want a gas that is going to play well with oxygen, that's going to mix well with it. If you have a stratified oxygen, then if you have too much oxygen in the lower troposphere, this could again lead to fires and explosions at the surface and also toxicity to life. But if the atmosphere is stratified in the other way, where all the oxygen is at the top, then whatever gas you have at the bottom, if there's too little oxygen in it in the lower troposphere, then that would make respiration impossible and advanced life cannot exist. So you need a gas with a good density match to oxygen. And my colleague and friend at Andrews University, who's a professor of chemistry there, Ryan Hayes, gave me some fantastic points about the importance of oxygen. So I'll give him credit for this. But he looked at all the different gases that could be chosen among various gases that we know of from planets and other celestial bodies in our solar system. And it turns out that nitrogen and oxygen are by far the closest. If you have a gas that's too light, then again, it'll sink up to the top of the atmosphere and oxygen will be at the bottom. You'll have a stratified atmosphere. If a gas is too heavy, it will not mix with the oxygen. Again, it will sink to the bottom. All the oxygen will go to the top. It'll become a layered atmosphere, and you will not have oxygen to breathe at the surface of the Earth. So nitrogen and oxygen have very similar gas densities. They mix very well. Nitrogen is a great choice. It turns out, though, that we just talked about 3 of the constraints that are needed for this other 78% of the atmosphere. There are many other constraints that have to be in that gas. It has to be non-toxic, non-flammable, hard to liquefy so it doesn't form oceans. It needs to be transparent to the right types of light that are needed for life on Earth. It needs to be non-reactive and acidifying. It needs to have low solubility in water, otherwise it'll dominate the oceans. It also has to be usable for living organisms, okay? And it turns out, this is again from my friend Ryan Hayes who did this. He's a chemist, he studies gases, he's gone through all these different options for other gases and found that only nitrogen fulfills all of these criteria. It's very impressive work he's done. Nitrogen fulfills every one of these criteria. It beats out all the other options for the 78%. And it Turns out that nitrogen, you may not appreciate this, being usable for living organisms is also absolutely vital for life on Earth. But why is that? Because nitrogen is an important atom in every single amino acid in your proteins and also all the nitrogenous bases in your DNA. Okay, so living organisms need nitrogen. It is a crucial element for life. And it turns out that there are certain types of bacteria and also certain plants which have symbiotic relationships with bacteria to take nitrogen from the atmosphere and fix it into their amino acids and nitrogenous bases. Those then allow nitrogen to enter the biosphere. We eat these organisms, we eat these plants, and we can get nitrogen into our own bodies. So nitrogen is crucial for life, and it's taken from the atmosphere by certain types of organisms, and it's very, very important. So one last point about Earth's atmosphere. There's actually a triple convergence of the electromagnetic radiation in the visible light spectrum that is 1, needed for photosynthesis and vision, 2, emitted by the sun, and 3, permitted to pass through the atmosphere. Okay, so this triple convergence is also vital for life. So what am I talking about here? Well, it turns out that light is just right, has the just right energy of the photonic energy to stimulate the kinds of biochemistry, controlled chemical reactions that can slightly modify organic chemistry. It has just the right activation energy to allow for these chemical reactions to take place. And we're talking about vision and photosynthesis. So visible light matches the energy of useful biochemistry. Photosynthesis uses the blue and red colors, frequencies of visible light, where the green is reflected. So that's what life needs to perform light-stimulated, and also forming vitamin D, I should add as well, forming life-necessary chemical reactions that are light-stimulated. Also, the sun emits a very broad spectrum of EM radiation, but the peak is in the visible range, just where we need it, okay? So you can find these kind of diagrams all over the internet. The peak of the wavelengths that are emitted by our sun peaks in the visible range of light, okay? And then, of course, the atmosphere has to allow this visible light to pass through. And this diagram shows the light that is blocked by the atmosphere, or I should say the EM radiation that is blocked by the atmosphere, but there's a huge hole in the blockage right where visible light is, and it allows it to pass through almost entirely. Okay, so light is just right is for this triple convergence of the energy output from the sun, the window that the atmosphere allows through, and the controlled chemical reactions of life. And also, as I said, vitamin D is stimulated by visible light. I'm gonna get as much vitamin D as I'm down here. They say vitamin D is really important during the pandemic. I haven't seen the sun in weeks in Seattle, let me tell you. So if you see me walking outside kind of like aimlessly for the next couple days, I'm just trying to get vitamin D before I go home. So there's a beautiful convergence between sun's energy, the atmospheric window, and EM radiation mediated by chemical reactions. Last topic here, Goldilocks to the third power. Let's put all this together and show how plate tectonics, water, and the right atmosphere help provide our planet with a global thermostat, okay? So it turns out that our planets, all these different elements we're talking about, work together to keep our planet at a constant temperature. Here's how it works. If it's too hot, then you get more rain and more weathering. That then tends to remove carbon dioxide from the atmosphere through a process where rainwater interacts with rock, and the earth then cools because you're losing this greenhouse gas. And what happens then, as the CO2 is removed from the atmosphere through the weathering of rock, it then travels down through streams and rivers as calcium carbonate and gets locked up in limestone sediments in the ocean, okay? And the earth cools, all right? So if it's too hot, we draw CO2 out of the atmosphere and the earth cools down. Then what happens is this limestone sediment, meanwhile deep in the earth, limestone sediment is subducted and melted, and then carbon returns to the surface in magma where it erupts. And what happens then? Well, if the earth is too cool, right, then there's less rain and less weathering, so you don't have this process of removing CO2 from the atmosphere. And as CO2 is erupted out of volcanoes through plate tectonics, it then builds up in the atmosphere, and the earth warms. So if you have too much CO2, it is then drawn out of the atmosphere. If you have too little, then it builds up, and it keeps the earth at a constant temperature. So I think this is really incredible that plate tectonics recycles carbon, atmosphere with CO2 greenhouse gas, and liquid water in large amounts allows this convergence, which yields a global thermostat that keeps our planet at a constant temperature. So Earth, let's talk about some of the properties that make Earth special. It's the only terrestrial planet in the solar system with a strong magnetic field. It's the only planet in the solar system with plate tectonics. It's the only terrestrial planet with large amounts of water. And it's the only planet that we know of that has an N2O2 atmosphere capable of supporting advanced life. And then finally, as far as this global thermostat goes, it's hard to imagine it happening anywhere else because of all these unique properties only appearing on Earth. So Earth appears uniquely well designed for life. In fact, a book came out a couple years ago titled Lucky Planet, which said that Earth was blessed with incredible good fortune, giving it all the right properties to sustain a complex and beautiful biosphere. Earth is a strange place, perhaps the luckiest planet in the visible universe. Well, this reminded me of a little scene from Star Wars where Obi-Wan Kenobi is having a metaphysical debate with Han Solo. Of course, Obi-Wan Kenobi believes in the Force. Han Solo is kind of like a materialist and a skeptic. And Han Solo says, look, I just need to use my own wit and my own guile to get by. I hope that the sound works. If it doesn't, I'll tell you what it says. But Obi-Wan says,
There's no such thing as luck.
Let me play this again.
In my experience, there's no such thing as luck.
Okay, so there you go. So we may be a lucky planet, but in my experience, there's no such thing as luck. We are not just lucky. We were designed to have all these parameters to create a place where life could exist. I'm going to fly through this last batch of slides here because this is something that's special that I've never actually presented this publicly. These are a different class of design arguments, you guys. These are aesthetic arguments for design. So take off your scientific hat for a moment and pretend you're in an art museum, all right? So this is a rock that I studied during my PhD, all right? It's a really ugly, boring-looking rock. I sampled this in Swaziland. What we do with every geologist has to go through this rite of passage. You sample a rock, you take it back, you have a thin section microscope slide created of the rock, and then you look at it under a rock microscope. And it turns out that when you look at these rock thin sections under microscopes, it is like looking at stained glass windows, okay? So God has like a 24/7 tour of stained glass windows, seeing what's inside of rocks. And we look at these rocks and we think that they're like the most boring rocks you might just kick down the street while you're walking along. But I'm telling you, you look at these rock microscope slides and they will blow your mind. They look like art that you would see in a museum. And so I have no art background whatsoever, but when I was going, these are all slides from my own PhD work that I did, and I felt like it looked like the kind of art that you would see in a museum. You have impressionists. I'm just gonna fly through these, okay? You have stained glass windows. You have, I guess you could call this modern art, something really funky or weird. You have Andy Warhol pop art with all these psychedelic colors. And then you have Cubism. So I'm no art expert, but I think that these are very different styles of art that are found in these, and it's really quite incredible. Some of these are beyond classification. I don't know what you would call this. Maybe somebody can tell me if this resembles some form of art, but I just think that these are incredibly beautiful. In fact, I showed these to a family member, and she broke down in tears after just appreciating the beauty that is found in the most mundane rocks you could possibly imagine, even things that look like characters. So thank you. I would say that Earth is not just a privileged planet, but it's a beautiful one. I've always wanted to say this in Texas. Thank you, and may the force be with y'all.